I want you to imagine that you are standing at the edge of a waterfall at night. You cannot see the river below. You cannot see the rocks. You cannot even see the mist. There is only darkness and the sound of water accelerating towards something hidden beneath you. Now imagine dropping a small wooden box into the current. At first, the box drifts normally, then it accelerates faster, faster. It crosses the edge and disappears from where you are standing. The story seems finished. The box has entered a region from which it will never return. But imagine that beneath the waterfall, instead of smashing against rock, the box reaches something stranger, a region where the river itself no longer behaves like water, where distance changes, meaning where the distinction between before and after becomes uncertain, where the equations you trusted to describe the fall simply stop giving sensible answers. That is where modern physics finds itself inside a black hole. From the outside, black holes are among the cleanest objects in the universe. Mass, spin, electric charge, a horizon. General relativity describes their external gravitational fields with extraordinary precision. We have watched stars orbit the supermassive black hole at the center of our own galaxy. We have detected gravitational waves from black holes colliding billions of light years away. We have reconstructed horizon scale images around supermassive black holes. Again and again, Einstein's theory works. But follow the equations through the event horizon and keep falling inward. Eventually, classical general relativity drives you towards something it cannot properly describe. A singularity, a region where curvature becomes infinite, where familiar equations cease to be predictive. For decades, we have drawn that singularity at the center of the black hole as though it were simply another object, a final dot, the end of the road. But an infinity in physics often means something very different. It may mean that the road itself has ended because the map has failed. And recently, quantum gravity calculations have continued to explore a far stranger possibility. Perhaps there is no singular point at all. Perhaps the center of a black hole becomes a deeply quantum region. Perhaps spacetime itself changes phase. And perhaps collapse reaches an extreme state and rebounds. Perhaps the interior connects to a white hole like future. Perhaps what we call the center is not a place, it is a transition. I need to be extremely precise. No telescope has looked inside an event horizon. No experiment has confirmed a quantum core. No observation has shown that black holes turn into white holes. And no existing quantum theory of gravity has been experimentally established as the final description of nature. But recent theoretical work continues to show that once quantum effects are taken seriously, the classical singularity may not survive. In one 2025 Physical Review letter study using unimodular quantum gravity, researchers found that demanding quantum consistency replaces the classical singularity and even the classical horizon structure in the model with a strongly quantum non-singular region. Other current approaches likewise investigate singularity avoidance or quantum bounces inside black holes. That is the door, because if the singularity disappears, then a black hole is no longer merely a cosmic grave, and it becomes something much harder to imagine, a laboratory where spacetime itself may change its nature. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to explore the places where established physics ends and the deeper structure of reality begins, you are in the exact right place. Now, I want you to imagine an old paper map. You draw a straight road across it, and the road passes through fields, villages, mountains, everything is clear. Then suddenly the road reaches the edge of the paper. You can make a terrible mistake at this point. You could conclude that the physical road ends there, but the road may continue perfectly well. Only the map has ended. Hold on to that image, because this is one way to think about a singularity. Einstein's general theory of relativity tells us that mass and energy curve space-time. A planet produces a small curvature, and a star produces more. Compress enough mass into a sufficiently small region, and an event horizon forms. Inside that horizon, every future directed path leads deeper inward. For a simple non rotating black hole described classically, continuing inward leads toward the singularity. The curvature grows without bound. Quantities that were finite become infinite, and classical spacetime itself becomes geodesically incomplete. This is often translated into the sentence, there is an infinitely dense point at the center, but that sentence contains more confidence than the mathematics deserves. General relativity is a classical theory. It does not include the quantum nature of matter and spacetime. We know that quantum mechanics becomes essential at microscopic scales. So when general relativity predicts infinities in a region compressed toward the Planck scale, many physicists do not interpret the singularity as a literal physical object. They interpret it as a warning. The map has reached the edge of the paper. Here is the hard truth. General relativity predicts the conditions under which its own description becomes incomplete. That is not failure in the ordinary sense. It is a signpost. Newtonian gravity did something similar. It worked beautifully until velocities became extremely high or gravity became extremely strong. Einstein did not prove Newton useless. He showed that Newton's theory was an approximation inside a deeper framework. Perhaps general relativity occupies the same position. Brilliant, precise, incomplete at the quantum core. To understand why quantum physics matters, I want you to imagine shrinking a spring, compress it, it resists, compress it further, the resistance grows. Now replace the spring with space-time. In classical general relativity, there is nothing fundamental that prevents collapse from continuing toward the singularity once matter is trapped inside the horizon. But quantum physics often introduces forms of resistance that do not exist classically. The uncertainty principle prevents particles from simultaneously having perfectly defined positions and momenta. Degeneracy pressure helps support white dwarfs and neutron stars. Quantum fields fluctuate even in vacuum. At sufficiently extreme scales, space-time itself may possess quantum degrees of freedom. We do not yet know exactly what that means, but several approaches to quantum gravity suggest that the smooth geometry described by Einstein may cease to be meaningful at the smallest scales, and the floor itself becomes granular or relational or probabilistic, depending on the theory. One approach is loop quantum gravity. It attempts to quantize geometry itself. Areas and volumes acquire discrete quantum properties rather than remaining infinitely divisible in the classical way. When related techniques are applied to highly compressed cosmological or black hole interiors, quantum geometric effects can become repulsive at extreme curvature and prevent the classical singularity from forming. Some loop-inspired models replace the singularity with a transition from a collapsing region to an expanding one. A bounce, hold on to that image. A ball falls toward the floor. Classical gravity says the floor is not there. The ball keeps collapsing forever into an infinite point. Quantum geometry says perhaps there is a floor after all, not a physical surface, a limit encoded in the structure of space-time. The ball compresses, reaches the quantum regime, and rebounds. Research in loop quantum gravity has explored black hole evolution into white hole-like configurations after quantum effects resolve the classical singularity. This remains a theoretical proposal, not an observed black hole process. Now, I want you to imagine a doorway that allows movement only one way. You can enter, you cannot leave. That is the intuitive image of a black hole horizon. A white hole, mathematically, reverses that idea. Nothing can enter from the outside, material can emerge. White holes appear as time reversed relatives of black hole solutions in general relativity. We have no confirmed astrophysical evidence that white holes exist, but some quantum gravity models ask whether the collapsing interior of a black hole could transition into an expanding white hole geometry. If such a process occurs, the black hole may not contain an eternal final singularity. It may contain a future. This is where your intuition is going to completely fail you, and it should. Inside a classical event horizon, moving toward smaller radius becomes as unavoidable as moving toward tomorrow. Outside the black hole, you can choose to move north or south. Inside, the causal structure changes. The singularity is not merely sitting somewhere in space like a rock. And in the simplest classical picture, it lies in your future. That distinction matters. You do not avoid the singularity by firing your rocket sideways. You encounter it as inevitably as you encounter the next moment. Now imagine quantum gravity removing that future boundary. Suddenly, the most important question becomes, what replaces it? A quantum region, another space time, a bounce, an evaporating core, a white hole, something for which words like space and time are no longer appropriate. We do not know, and that uncertainty is where the mystery lives. I want you to imagine an ocean. From far above, it looks perfectly smooth, a blue surface, continuous. Move closer, and you see waves. Closer still, and you see droplets. Closer again, and molecules, atoms of quantum fields. The smoothness existed only at one scale. Hold on to that image. Space time may work similarly at the scales of planets, stars, and even ordinary black hole horizons. Geometry behaves smoothly. General relativity describes that smooth ocean extraordinarily well, but deep inside, where curvature becomes extreme, the microscopic structure of spacetime may become impossible to ignore. The ocean may reveal its molecules, except we do not yet know what the molecules of spacetime are. This is why black holes are so important, and they force quantum theory and gravity into the same room. Ordinary quantum mechanics largely assumes a space-time background. General relativity makes space-time dynamical. Black hole interiors push both theories into conditions where neither can be ignored, and the disagreement becomes violent at the singularity. And this brings us directly to another paradox. Information. I want you to imagine writing the complete contents of a book onto microscopic pieces of paper, every word, every letter, and then throw the pieces into a furnace. Ordinary physics tells us that although reconstructing the book may become practically impossible, the underlying quantum information should not simply vanish from reality. Quantum evolution is expected to preserve information and now replace the furnace with a black hole. Matter falls in, its details disappear behind the horizon. Then Hawking's quantum field calculation tells us that black holes should radiate very slowly. Hawking radiation over unimaginably long times. An isolated black hole can lose mass and evaporate, but Hawking's original semicosmic calculation makes that radiation appear thermal. If the black hole ultimately disappears and the radiation contains no recoverable information about what fell in, quantum mechanics seems violated. This is the black hole information paradox. It remains one of the central conceptual conflicts linking gravity, thermodynamics, and quantum mechanics. A 2026 review in Nature Reviews Physics highlights precisely this tension. Hawking's semicosmos picture appears to erase information, while unitary quantum mechanics says information should be preserved. The singularity and the information paradox are not identical problems, but they may be connected. If the singularity is a place where information literally ends, unitarity becomes difficult to maintain. If quantum gravity replaces the singularity with a non singular region, perhaps information can remain encoded in the full quantum state. Perhaps the interior geometry stores it. Perhaps correlations in Hawking radiation return it. Perhaps what we call inside and outside are not independent in the way semicosmos reasoning assumes. This is where modern work involving quantum neutrino surfaces and so-called islands has transformed the theoretical discussion. Calculations and simplified gravitational models have reproduced the expected page curve. Radiation entropy rises and then eventually falls in a way compatible with unitary evaporation. That does not yet provide a complete microscopic description of a real astrophysical black hole, but it tells us something profound. Gravity may encode information in ways our classical concept of location does not anticipate. The inside may not be as separate from the outside as it looks. Think about that. The event horizon is supposed to divide space time outside, inside, visible, hidden, but quantum information may not respect that division. In the naive way, the geometry could be emergent from deeper entanglement. Parts of what semi-colloquial space-time labels interior may be encoded in degrees of freedom associated with radiation or exterior regions. This is not science fiction. It is one of the active frontiers of quantum gravity research, and it leads to perhaps the strangest possibility of all. What if black holes are hiding not an object, but a failure of locality itself? I want you to imagine two rooms connected by no visible hallway, and you place a book in one room. Later, information about the book appears encoded in the wallpaper of the other room. There is no ordinary path connecting them. From the perspective of classical geometry, this seems impossible. But quantum gravity repeatedly hints that space-time connectivity and quantum information may be related more deeply than everyday locality suggests. Ideas involving holography push this even further. In holographic theories, gravitational physics inside a region can be equivalent to a non-gravitational quantum theory living on a lower dimensional boundary. The volume may be encoded by the surface. A three-dimensional gravitational world can emerge from quantum information arranged elsewhere in the mathematical description. Now stop, because this is where the phrase black holes are hiding something stranger becomes almost literal. Perhaps what they hide is not a tiny exotic object at the center. Perhaps they hide the fact that space-time is not fundamental. The black hole interior may be the place where the illusion of smooth geometry breaks down. The singularity may disappear because geometry itself dissolves before infinity is reached, not an infinitely dense point, a region we're asking where becomes the wrong question. Here is the hard truth. We do not have observational evidence for that conclusion. The exterior behavior of astrophysical black holes remains remarkably consistent with general relativity. Gravitational wave observations have subjected black hole mergers to increasingly precise tests, including measurements consistent with the Kerr description of rotating black holes and Hawking's classical area theorem. So nature gives us a strange split. Outside the horizon, Einstein wins again and again. Deep inside, Einstein predicts its own breakdown. The revolution may be hidden precisely where direct observation becomes hardest. And that sounds hopeless, but perhaps it is not, because black hole interiors can influence external physics indirectly. Imagine a bell. You cannot see inside it. Strike the bell and listen. Its tone depends on its shape, its material, and its internal structure. Black hole mergers ring in space-time. After two black holes collide, the final object settles by emitting gravitational waves in a phase called ring down. The frequencies and damping times of those oscillations depend on the black hole's properties. General relativity predicts them precisely. If the near horizon structure differs from the classical picture, some speculative models predict additional signatures, echoes, modified ring down modes, small deviations from Kerr geometry. So far, no universally accepted gravitational wave evidence has established exotic quantum structure around astrophysical horizons, but increasingly sensitive detectors provide a way to test the exterior consequences of theories that once seemed permanently inaccessible. The hidden room may shake the walls. That is the experimental hope. Future gravitational wave observatories will observe black hole mergers with far greater precision. Space-based detectors will explore different mass ranges. Horizon scale imaging will improve. Precision measurements of stars and gas orbiting black holes will tighten constraints on deviations from general relativity. If quantum structure leaks into observable scales, even slightly, we may eventually catch it. And the trick is that most quantum gravity effects are expected to become dominant near the Planck scale. That scale is absurdly small, roughly 10 to the minus 35 meters, far beyond any direct laboratory microscope. Black holes compress nature toward exactly the conditions where such effects may become important. They are cosmic accelerators built by gravity. This is why theorists obsess over their interiors. The center of a black hole may be one of the few places in the universe where spacetime itself is forced into a quantum state. Now, I want you to look around the room you are sitting in right now, and the floor appears solid, the walls appear continuous, space seems empty and smooth, time appears to flow, and all of this is the macroscopic world. But physics has repeatedly shown that macroscopic reality is built from layers that look nothing like the surface. A table is mostly quantum fields. Matter is not made from tiny hard balls. The particles behave as excitations of fields. Temperature emerges from microscopic motion, pressure emerges from collisions. Perhaps space time is another emergent layer, and perhaps a black hole is what happens when we push that layer until it tears. That would explain why the equations produce an infinity. We keep extending the smooth fabric into a regime where the fabric no longer exists. Imagine describing water waves after every water molecule has been removed. The equations of fluid dynamics would fail, not because reality failed, because water had stopped being a fluid. Perhaps the singularity is the same kind of mistake. And we ask classical geometry, what happens after geometry has stopped being classical? The answer comes back infinity. We call it a singularity. Quantum gravity may eventually teach us to translate that infinity differently. This description is no longer valid. That is less dramatic than an infinitely dense point and much stranger, because then we need another ontology. What is there when space time is gone? Quantum states, networks, strings, and loops, entanglement, something else. Different theories give different answers. String theory replaces point like fundamental objects with extended strings and contains mechanisms through which black hole microstates can be counted in certain special cases. Loop quantum gravity quantizes geometry and often replaces singular behavior with quantum transitions. Asymptotic safety approaches investigate whether gravity becomes well behaved at extremely high energies. Non local and higher curvature theories can produce regular black hole solutions without classical singularities. Recent work has even shown that certain non perturbative gravitational frameworks forbid singular black holes, except under unphysical limits. These ideas cannot all be the final story in their current forms. Some may be wrong. Some may describe different approximations to a deeper theory. The important fact is that the singularity itself is no longer treated as sacred. It is a target, something to resolve. This is the moment everything changes, because the question, what is inside a black hole, used to have a simple popular answer, a singularity. Now, the scientifically mature answer is we do not know. Classical relativity predicts a singular boundary. Quantum mechanics tells us that classical reasoning must eventually fail. Several serious theories replace that boundary with something non singular, and experiments have not yet told us which, if any, is correct. That uncertainty does not weaken black hole physics. It makes black holes one of the most important laboratories in theoretical science. Imagine Newton in the 17th century. He could predict planetary orbits, but he did not know that gravity would eventually become geometry. Imagine Maxwell. He unified electricity and magnetism without knowing photons would later appear in quantum theory. Imagine Einstein developing general relativity without knowing that black holes would become central to the search for quantum gravity. Every successful theory opens a door it cannot walk through. Black holes may be Einstein's door. On one side is smooth space time, on the other is whatever space time is made from. Now I want you to imagine falling into a supermassive black hole. Choose one large enough that the tidal forces at the horizon are initially mild. You cross the event horizon locally in idealized general relativity. There may be no dramatic wall, no glowing surface, no alarm. The horizon is not necessarily a material membrane. You simply pass a causal boundary. Behind you, escape becomes impossible. Ahead, classical geometry drives you inward. At first, the world remains describable, and then curvature grows, your future narrows, quantum gravity effects become impossible to ignore, and here the textbooks fall silent. Does space time terminate? Does geometry bounce? Does time itself change character? Does information pass through another phase? Is the interior encoded non locally? Does the distinction between inside and outside cease to be fundamental? Nobody knows. The most honest map contains a blank region. And perhaps that blank region is the most important territory in physics. Hold on to the waterfall. We began by watching a box disappear over the edge. From outside, the event horizon seemed like the end of the story. But perhaps the horizon is merely where our access ends, not where physics ends. Deep below it, classical spacetime may undergo a transformation as radical as ice becoming water. The object is still physical, but the phase has changed. So, this phase transition metaphor appears in many quantum gravity discussions because we already know that collective descriptions can fail when conditions change. A magnet loses magnetization above a critical temperature. Matter changes phase under pressure. The early universe itself may have passed through symmetry breaking transitions. Why should spacetime be immune? At extreme curvature, perhaps geometry enters a new phase. If so, the black hole interior is not a destination. It is a state of matter or geometry for which we do not yet possess the correct language. Think about the sheer weight of this. Every black hole in the universe may contain a region where our concept of space time breaks down. Stellar mass black holes, supermassive black holes, the remnants of ancient stars, the giant dark objects at galactic centers, millions upon millions of natural laboratories. From the outside, they look extraordinarily simple. Inside, they may hide the deepest complexity nature can produce. There is something almost inverted about that. The simplest exterior, the most mysterious interior. A black hole has very few externally measurable classical parameters. Yet, its quantum microstate may need to encode an enormous amount of information. This tension is captured by black hole entropy. The entropy of a black hole scales with the area of its horizon, not its volume. That single fact helped inspire the holographic principle. Information capacity behaving like area rather than volume suggests that our ordinary intuition about where information lives may be fundamentally wrong. The horizon may not merely hide the interior, it may be telling us how the interior is encoded. The surface and the volume may be two descriptions of the same underlying quantum system. Now, the phrase hiding something changes meaning again. Maybe the black hole hides a quantum core. Maybe it hides a bounce. Maybe it hides a white hole. Maybe it hides no conventional interior at the deepest level. Maybe what it truly hides is that space itself is an emergent bookkeeping device for quantum information. We do not know, but each possibility is more radical than a tiny, infinitely dense point. That is why I find the singularity almost comforting. A singularity is frightening but simple, infinity, and nothing more to explain. Quantum gravity refuses that comfort, and it tells us the infinity may be the beginning of the real question. Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless distinction between what theory permits and what observation has actually established. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel there, you help make these long-form explorations possible. But before we end, return with me to the images we carried through this journey. The waterfall taught us that crossing a horizon is not necessarily the end of physics. The paper map taught us that a singularity may mark the failure of a description rather than a physical point. The compressed spring introduced the possibility that quantum effects resist unlimited collapse. The bouncing ball showed us how a quantum transition might replace the classical singularity. The one-way doorway introduced the strange possibility of black hole to white hole evolution. The ocean taught us that smooth spacetime may conceal microscopic structure. The burning book gave us the information paradox. The ringing bell showed us how hidden interiors might someday reveal themselves indirectly, and the torn fabric reminded us that perhaps space-time itself is only an effective layer of reality. Scientists have not discovered what lies at the center of a black hole. No one has seen a quantum core. No one has confirmed a bounce. No one has detected a white hole. But modern quantum gravity research is making one thing increasingly difficult to ignore. The singularity may not be the final answer. It may be the place where our current answer stops working. And if that is true, then black holes are not hiding a point of infinite density. They may be hiding the transition between space time as we know it and whatever reality is made of underneath, and the door remains closed, but the equations are beginning to tell us something strange about what may lie behind it. Perhaps the darkest objects in the universe are not graves after all. Perhaps they are boundaries, places where classical reality ends, quantum reality begins, and the deepest mystery is no longer what falls into a black hole. It is this